So, welcome to this class. In the last class we have just gone to the indexing patterns and also about the Kikuchi patterns, which are used to go from one zone to another zone by keeping the G vector same, and also we talked about different zone axes. In this class what we do is we will talk about the image contrast, how we are getting the image contrast in TM, and there are three different types of image contrast what we get it. The first one is mass thickness contrast, the second one is your diffraction contrast, and the third one is you can get the phase contrast. Okay. So, here the mass thickness contrast is related to your angular range and the energy spread that is affected by elastic and inelastic scattering. Okay. So, here we can use also the aperture to stop all the electrons, which are scattered by scattered by an angle alpha. Okay. So, this is a mass thickness contrast. So, if you have higher mass, so if you have a sample and if your area, this particular area contains higher atomic mass element, higher atomic weight or lighter, then you will see that the scattering from this higher atomic mass or higher atomic weight will be much higher. So, you will get a dark contrast in this region and you will get a bright contrast in this region. Okay. Similarly, the thicker samples, the thicker regions of the sample will have a dark contrast, or the thinner samples will have a bright contrast. This is a very simple mass thickness contrast. Okay. So, here usually the regions of the specimen which are thicker and have high density will scatter more strongly, and this will appear as a dark in the image. Okay. And this is very important for biological samples. Okay. So, what we will do is in the biological sample, what they do is usually these are amorphous. So, the sample regions which are important, they will do what they will do, they will stain by heavy metals. For example, they will use mostly osmium, and this is used to decorate the specific feature that leads to the higher contrast during imaging. Okay. So, this is a example for the mass thickness contrast. So, all specimens, either this is a amorphous region, you will have a crystalline region, biological or inorganic samples. Okay. So, these all whatever the contrast you are getting, you can also superimpose. Okay. So, here both, as I told you, both elastic and inelastic scattering occurs, which actually resulted in the change in the direction by small amount. Okay. So, this is related to your mass thickness contrast. What is the diffraction contrast? So, diffraction contrast corresponds to the principle related to the diffracting intensities, okay, and this is the most important contrast which we use in the most regularly in the transmission electron microscope. So, it comes from the diffracting electron leaving the lower surface of a specimen, of you can tell also as a crystalline specimen, and these diffracted beams are actually intercepted by the objective aperture in the lens system. Okay. So, some of the diffracted rays they are actually intercepted by the objective aperture. So, they can also prevent from contributing to the image. So, this diffraction contrast is dominant when it is greater than 15 angstroms. The object details or the feature details which you want is the more than 15 angstroms. Now, as I told you that diffraction contrast, if you remember, there is an objective lens, okay, then at the back focal plane you are getting a diffraction spot with a transmitted spot, and these spots at the back focal plane you can keep an aperture of any of these spots, so that you can remove the contribution from the imaging, correct. So, those diffracted spots will be absorbed by the objective aperture. So, whatever image it forms on the screen will not be from that particular diffracting planes, correct. This way you can actually do the bright field and the dark field imaging, or you can also do the center dark field imaging. I think in the last class I have briefly thought about this, that how to take the bright field and dark field image. Diffraction contrast is also important for dislocations, if there is a presence of stacking faults and there are other defects. Okay. So, here if any compounds are there which is having a different composition, they can actually alter the structure factor f theta. So, it will directly affect the intensity, correct. So, this is a type of. Then one more important parameter is tilt angle, okay. So, it will produce a tilt angle of the specimen. Then if your sample is not flat, if it is a bent sample, then what will happen, those bent region it might be Bragg diffracted, due to which you will get a dark regions, okay. So, this so these are called bend countors. Okay. Now, the third contrast is called the phase contrast. Okay. Phase contrast, here the electron which leaves the specimen after interaction, these electrons which leave the specimen after interaction of the diffraction, they actually recombine to form an high resolution image. Okay. So, it directly resembles to the phase contrast present at the exit surface of the specimen. Okay. And this phase contrast, the difference in phase contrast is converted to the intensity differences in the image. Okay. So, usually this phase contrast is used if you have sample feature, if it is less than the 10 angstroms. Okay. So, these are the different types of image contrast which we can get in a transmission electron microscope. Now, we will understand that what is the how your intensity is generated on the image. Okay. So, what we can do is your total intensity can be given by I0 plus Ig. Here I0 resembles to the direct beam and Ig is the diffracted beam. Okay. And the Ig, the diffracted beam. So, first we will call about the diffracted beam. The can be proportional to the phi g, which is called amplitude. Okay. Amplitude, and it is given by pi t by psi g square dot sin square pi t S effective divided by pi t S effective whole square. Okay. So, here there are certain terms which we need to understand. So, we will just describe one by one. Okay. And this terminology is very important to understand the diffraction contrast. Okay. And this particular equation Ig equal to, this is the solution to calculate the intensity of diffracted beam. Okay. So, here there are several terms in the equation. The T is thickness, of sample. Psi g is the extinction distance of selected g vector. Okay. So, here the psi g is given by pi v cos theta b divided by lambda f g. So, here V is the volume of the unit cell, theta b is the Bragg's angle, lambda is the wavelength of beam, and Fg here is the structure factor. Okay. So, for any given material, for any given sample material, in this psi g equation, your volume, lambda and Fg is known. So here the only thing which is unknown is theta b, which is a Bragg's angle. So your psi g is proportional to your theta b. So psi g for different planes is different. For example, the psi g of 100 is not equal to psi g of 111. Okay. So this is the definition of extension distance. So more physical interpretation of extension distance, I will come to that in the later, but to understand this equation you have to remember that this extension distance is directly proportional to your theta b. So your extension distance for different atomic planes are different. Fine. Now there is another important term in this equation is S effective. Okay. This S effective is called effective excitation error. Effective excitation error. What is effective excitation error? Effective excitation error is given by S effective is equals to root of S square plus 1 by psi g square. Okay. What is S here? S is the deviation parameter, is the deviation from perfect Bragg's condition. Remember in the last class I have described you about the railroads, correct? And when your sample is present here, if you have some crystallographic planes, if your beam is interacting and it is forming certain spots, these spots because of the thickness, Z thickness, are few unit cells, then what will happen? The intensity along the Z will get broadened up. So you will see the railroads. But in the x and y direction, as the unit cells, number of unit cells is infinite, you will see a strong spot. So in x and y direction you will see a very sharp spot, in y direction you will see a very sharp spot, but in the z direction you will see a very diffused intensity, and this diffuse intensity is related to your appearance of the railroad. So maximum will be at the center and it will diminish, and the deviation from the Bragg's condition or is called S, which is a deviation factor. So at the center of the railroad S is equal to 0. If the evolved sphere cuts at the center, it means that S is equal to 0. If the evolved sphere cuts at the top, you can tell S is greater than 0. If it is greater at the lower, you can tell S less than 0. Okay. So this is called deviation factor from the Bragg's condition, and this is very important in the diffraction, contrast, imaging of defects. Fine. So that particular S value is this particular term. Okay. Now here we can see that even though the evolved sphere cuts the railroad exactly at the 0 position, means S equal to 0, your S effective is not equal to 0. Okay. So when S is equal to 0, your S effective becomes 1 by psi g. Okay. So if your sample is very flat, means there is no bending. Okay. So it means that if your sample is bent, what will happen? If this is your incident ray, this is your crystallographic plane, at this position if S equal to 0, because of the bending your S will vary while going along the sample surface because of the bent nature. Your S changing means your evolved sphere is not cutting at the center of the railrod, it is going away from the center of the railrod. Okay. So imagine that if your sample is very flat, there is no bending and S is equal to 0, then S effective is 1 pi psi g, then your intensity Ig becomes pi t divided by psi g whole square dot sine square pi t divided by psi g divided by pi t divided by psi g. This is just keeping the S effective value in this equation, correct. Now with this what you can do is you can cut this position, you can cut these positions. Now you will get intensity of the diffracted beam is directly equal to sine square pi t by psi g. Okay. With this what we infer is Ig is function of sine square pi t and also the function of thickness. Okay. So if your total intensity is 1, which is equals to I total, then your incident intensity plus Ig, then your I0, the undeflected intensity is equal to 1 minus Ig. Okay. So you can see that here by this equation, if your thickness is near to psi g, then what will happen? Your intensity becomes 0. Understand? That is why psi g is called the extinction distance. What is extinction distance? It is the distance from the sample surface. It is the distance from the sample surface where your intensity goes to 0, again it rises, again goes to. So this value particular is called the psi g value. As the definition of psi g, this psi g value is different for different atomic planes. Okay. So means the intensity of the diffracted beam Ig changes along the thickness while passing through it. Okay. And when your thickness is psi g, then your intensity becomes 0. Okay. So if there is a 2 beam condition, what is the 2 beam condition? Only the transmitted spot, only the diffracted spot. Means your evolved sphere is cutting only along the transmitted and the diffracted spot. So you are tilting your sample in such a way that your evolved sphere is only cutting the transmitted and diffracted spot. So even one set of plane is diffracting, your sample thickness, if it is psi g, then there will be a no diffraction spot. You will not see any spot, any diffraction spot, you will always see only the transmitted spot. Why? Because your thickness is near to the psi g, which is the extinction distance. Okay. Now I will rewrite this equation equal to sine square pi t by psi g. Now as we know that any wave equation, the total wave equation is given by, here phi 0 is the amplitude and omega is the phase difference, omega is the phase. Fine. Based on this equation, your total wave function can be written as phi 0, which is for the incident beam, e raised to the power 2 pi I x naught dot r plus phi g1 2 pi I x g1 dot r. This is for the spot g1. Like this you can write equation for each diffraction spot. If you are assuming for the two beam condition, we should consider only these two equations, assuming that it is in a two beam condition. So your two beam condition, your equation will become only the incident beam and the diffracted beam. Okay. Now how much, if to quantify how much magnitude of electron beam during travelling across the sample thickness. So to calculate that, what you have to do is, you have to, so there are two important terms, okay, which are called and d phi 0 by g, and these equations are called Darwin-Hovey-Whelan equations. Okay, and this equation is represented by d phi g by del z. So it is the intensity of the diffracted beam changing with respect to your z, with respect to your, if your sample thickness with respect to your z changing is given by, if you differentiate this particular equation, you will have value of phi by psi g, phi naught 2 pi I e raised to power 2 pi I x naught minus x d dot r plus phi I by psi g. Similarly, for the transmitted, d phi 0 by del z is equals to phi I by psi g phi 0 plus pi I divided by psi g phi g 2 e raised to power 2 pi I x d minus x naught dot r. Okay. So here the x naught minus x d is the change in vector of phi g when the beam scatters into phi 0. Okay. So for example, if you have a sample thickness, you have an intensity I 0 and this is your transmitted, this is your diffracted I g. It is possible that the I g can diffract again, and again it can contribute to the incident beam. Okay. So it is the change in vector of phi g, beam scatters again back to the phi 0. Similarly, x d minus x naught is the change in vector phi 0 which scatters back to the phi g beam again. Okay. And these equations are the solution, the intensity which we have given this equation is the solution to these this equation. So based on the definitions, what we tell is the psi g is a constant which is defined as the critical distance in a perfect crystal at which the transmitted intensity falls to 0 again before increasing. So this is called extension distance. Okay, and in this term the e raised to the power 2 pi I s x d minus dot r is this particular term is called the phase factor from the scattering process. So the first term in each equation is the scattering from the undeflected beam, and the second term is the scattering, the second term, first term, this is the second term, this is called first term, and the second term is represented by the scattering from the diffracted beam. Okay. So here the amplitude of each wave changes as the wave propagates through the crystal due to the contribution from the others. Okay. So based on the equation, what we see is okay. So here these are the two equations, and I have shown the solution of these two equations related to phi g, Ig intensity is a function of sine square and also the thickness, and you can see that if there is your sample thickness and if your incident beam is falling, then if you divide these into several volumes of dz, then each volume will have a diffracted intensity and the transmitted intensity, and while travelling this beam it might possible that the diffracted intensity again diffracts and which contributes to the phi 0, and again it can diffract to contribute to the phi g. Okay. And there is that is why the intensity of I 0 and I g changes along the thickness. Okay. And the distance at which your intensity of I 0 changes to 0, it means that I 0 changes to 0 or the diffracted intensity changes to 0 is called psi g, and at the half of the psi g you can see that the intensity of the transmitted beam becomes 0. So if your thickness is equivalent to this particular value psi g, then you will not see any diffraction, even though you will not see any diffraction spot on the back focal plane. So based on this particular equation of the intensity, now your sample cannot be ideally a flat sample. Okay. Your sample might possible that at the edge your thickness is changing as you go away from the edge, correct. So consider this schematic where it is shown that a sample edge which the thickness varies if you go into the sample. Okay. So this is your z. Now as I told you that at psi g value you will see Ig is almost equals to 0. So, if the thickness of the sample, so your thickness is changing and the locations where the thickness is equals to psi g, what you see is in the diffracted intensity you will see the intensity of Ig becomes 0 and suddenly it will again increase and it will become bright. So, you will see a continuous fringes of dark and bright fringes while your thickness is changing. So, in the right side I am showing an image of a TM image where you can see that you are seeing a thickness fringes. These are called thickness fringes. Okay, and these thickness fringes, the distance between the two bright intensities or difference between the two dark intensities, it is directly related to your which psi g you are considering it during your diffraction. Okay. So, if you orient your crystal in such a way that your g vector changes, so it is possible that the thickness, it is always there that the thickness, the distance between the two bright fringes will also change because your psi g value will change. So, it might possible that you can get the higher number of thickness fringes. You can see that the psi g value for aluminum for different crystals, it is written here, these are in the Armstrongs. You can see for the 111 the psi g is 556. So, if you are in the orientation of 111, the G condition, then you can see that the large number of thickness fringes due to the change in the thickness. Okay. Similarly, the reverse will happen when you are doing the bright field imaging. So, wherever the psi g becomes 0, your I0 becomes maximum. Correct. This is the reverse of the, so you will see the inverse contrast in the dark field and the bright field. Now, in the term Ig, in the term of Ig, we see another term which is called Ig is equals to sin square. There is another term which has a sin square pi t S effective divided by pi t S effective whole square into pi t square by psi g. S effective. Okay. So, this S effective also is given by S equals to root of S plus 1 by psi g, correct, whole square. Now, as your sample, we are assumed that the sample is flat, there is no bending or the local bending. So, if your sample is bent, imagine the sample, this is your sample and your thickness is constant, but as your beam falls, incident beam falls, what will happen, that even though your planes are not in the Bragg's condition, at a certain value it can be Bragg diffracted, or it might possible that the S will vary as your bending angle increases, correct. If it is a Bragg diffracted at S equal to 0, it might possible that that same planes at a certain again location, you will see that the S changes. As S will change, it will have a direct effect on the intensity psi Ig. So, you will see the bend contours in your samples. So, if there is an appearance of bend contours in your during imaging, whether it is in the bright field or the dark field, you will see that the bend contours looks like this. Okay. and the sample is bent, due to which these bent contours appears. This is due to the same thickness, but S varies, correct. So, these two types of contrast always you will get in the TM foils, either it is bent contours, either it is thickness fringes. Okay. So, with this I will end this class now, which we have gone through briefly about the bend contours, about the thickness fringes and the intensity. In the next class I will go through how these conditions can be used for the defect analysis. So, I will just briefly touch on those topics, so that you will see that actually you can use this weak beam or S, the S positive or S negative, you can use these to get the diffraction contrast from the dislocations which are present in the crystal lattice. Thank you.